A 2-3 tree is a self-height balancing tree. And first of all, I like to mention why a self-balanced tree is good and where does 2-3 tree come from in the first place. Well, a tree that is height balanced by itself is good because if a tree is not self-balanced, whenever it has a node, it might, when doing insertion, it might insert it to the left. If we want another insertion, it might go to the left again, and left again, left again, left again, and left again. And in this example, we might have 8, 7, 6, 5, 4, 3, 2. And if we were to insert another node with the key 1, we have to go all the way down from the root to the very bottom in this skewed tree, and we insert a node 1. This going all the way down causes O (n) of time, which is very, very long time. And if we were to have a height balance tree, it will then look something like a triangular shape. With some mechanism, it is going to balance the tree itself. And in this case, we already have 7 nodes. If we were to insert 1, it goes only this deep to this place, and we insert 1, causing only log n time, which is a huge improvement. So this is why a balanced tree is important. For either search, insertion, or deletion, we're going to have a better time compared to a non-height balance tree. And now to the part where 2-3 tree comes from in the first place. We know that in AVL trees is a height balance tree as well. And it balances the nodes using 4 kinds of rotating operations. Just to give an example, if we appears to have this skewed tree again, it uses a rotation and rotates the structure and makes it balanced. This is one of the rotation type, and there are 4 rotation operations in AVL tree. And the point is that in the AVL tree, it balances itself using these 4 rotating operations. And the key idea where 2-3 tree comes from is that can we maintain a height balance tree while not using the 4 rotation operation in AVL trees, since the AVL tree rotating operation is more complicated. And so the answer is yes. If we can allow a node to accommodate more than 1 keys, we are able to solve it. And so now we have a 2-3 tree. The 2-3 tree allows 2 children or 3 children. And by just observing, we could see that if a node have 2 children, it has only 1 key. If a node have 3 children, it has 2 keys. So in this 2-3 tree, we have only a 1 key node or a 2 key node. Okay, now to the searching part. Just like all the search trees, when we do a searching, the left is going to be less than the root value, and the right is going to be greater than the root value. And it is just this simple. Now to the insertion. of a 2-3 tree. Well, we know that in a 2-3 tree, we could only have a one key node, or a 2 key nodes. So in the case where, well, any nodes other than this is not allowed. And so let's just dive into an example directly. We're going to insert from 1 to, let's see. Okay, we have 1 in the first place. We inserted 1, and it's all good. And now we insert 2. We see we are able to have a 2 key node. This is a 2 key node. Okay, now to the 3. We want to insert another key, but notice that we only allows a 1 key node or a 2 key node. So this is not allowed. What we do is we do a split operation. A split operation, it literally do what the name suggests. It splits the not allowed node into a right and a left, and pushing the middle node to the top, just like this. It pushes the middle node to the top, and now connecting it. You see, we've done a split operation, and it is now balanced. And to inserting 4, we see we have a 1, a 2, a 3. Where do we want to insert the 4? We do just like all kinds of insertion in a tree, we go down, because we want to insert 4. 4 is less than 2. 4 is greater than 2, and 4 is greater than 3. We know it want to insert right here, and it is still balanced, which has at most 2 keys. And then we insert 5. We have 2, we have 1, we have 3 and 4. We go down this path, since 5 is greater than 2 and greater than 3, greater than 4, we want to insert 5 right here. Notice, once again, we've come to a structure that is not allowed in this 2-3 tree. What do? We do the split operation. Once again, we split this part into 3 to the left, 5 to the left. We push the 4 up, and once we push this 4 up, it is going to be connected with 2. Since you see 2 and 4 as a big node is allowed in this structure. And samely, as the same way we connect the 1, we connect the 5, and notice that we have this part where it connects to the 3. So it goes like this. This part is less than 2. This part is in between 2 and 4. And this part is greater than 2. It's greater than 4. Okay, now to inserting 5. Now to inserting 6. We have 2, 4, 1, 3, 5. Now inserting 6 is just as simple. Inserting 7 now comes to this structure. 5, 6, 7. Notice once again we've come to a structure that is not allowed in the 2-3 tree. And we do a split operation. Once again, we pushes the 6 up to here, And then notice that we will do this recursively. And so if we push the 2 up here, it will come to a 2 4 6 structure, which is again not allowed in a 2 3 4 tree. So we do it recursively. We do a split operation up again, making a 2 6 4 structure connecting the bottom, and finish it off with connecting everything that we have. And this is how you do insertion. Now to the deletion part. The deletion part, well, you see, we might, I forgot to mention that whenever this not allowed structure happens, it is called overflow. It is called overflow, which in this case, in this 2 3 tree structure, we could only have a 1 key node or 2 key nodes. So whenever a 3 key node we want to have a 3 key node, it overflows, and we need to do a split operation in order to make it to the allowed structure that we have in this tree. And in the case in deletion, what happened is an overflow, but an underflow. An underflow in a 2 3 tree occurs when deleting a node, and after deleting it, the node does not have enough key that is allowed. For example, if we delete 32 in this case, it then becomes an empty node. But we know that in this tree, we allow only a 1 key node or a 2 key node. So an empty node is not allowed. And the trick to do this is there are two ways to deal with this. Either you borrow from sibling, or you could do a merge from a parent node. In this case, we see that the sibling of this empty node is 41 and 49. If it borrows a node, it becomes a 1 key node, which is still a valid node. And so this is what we do. In this subtree, which we want to balance, you see, after the borrowing key, the tree is going to look something like this. And in order to make it still searchable, the only way of putting the value is that the 49 will stay right here, the 41 will go up, and the 38 will stay right here. And this is a balanced tree. And so the empty node borrows a key from its sibling, and it balances itself. Now after this, if let's do another one, right? We now have 41, 38, and 49. And so the same thing applies. If, say, this time we were to delete 20, we delete this node, and since it is now a 1 key node, it is a valid, it doesn't underflow, so it is all good. And next, if we were to delete, say, Let's delete 24. If we were to delete 24, well, first of all, the tree now becomes this. If we were to delete 24, you see it becomes an empty node, which is not allowed, so it is underflowed. And so it looks at its sibling. The sibling does not have any keys to borrow. So we come to this way of merge from parent. What does this mean? We see the parents, we take this node, we take it down, and we merge the left and the right. In this case, just by looking at this 3 node, and if we take the 18 down, the 17, and the empty, and we merge it, it will then become a big node with 18 and a 2-key node with 17 and 18. Right? Rewriting this, and this is called a merge operation. So the entire tree will now become, we have the 16 right here. The 14 is still right here, and it merges to a 17 and 18. And everything up here is still the same, right? The 10, the 30, 41, 38, 49, 3, 27, and 20 and 7, right here. It is still a valid tree. It is well balanced. Okay. And so, in the case where you might wonder, when doing a merge operation, we have a parent node come down, and if ever after the parent node come down, it becomes underflow, then of course we have to do we have to deal with this empty thing again. We look at the sibling. If it could borrow, you take it from the sibling. Otherwise, you do the same merge operation up again. And so it literally propagates the empty node from the leaf to the top, where it then satisfy the tree property. And at most, it might goes up to the root, and then overall decreasing the tree height of 1. But yeah, we could do some other example. If we were to have 18 removed, it is just as normal. If we were to have 17 removed right now, it's going to be empty. It looks at its sibling, doesn't have any node to borrow. We look at its parent. We have the parent node come down. We merge the 14 and this down. This node right here becomes 14 and 16. Now the problem occurs to this empty parent now. So yeah, you see, we literally propagate the empty node to the top. So the 41 right here, the 38, the 49, all these are still the same, right? And now we need to deal with this empty node. We look at its siblings. There's nothing to borrow since they are already a 1-key node. So what do? We borrow from the parent. We look at the parent, 10, 30, and we borrow a key from the parent. In this case, there are 2 key, and suppose that we take the 10 in this case. We borrow the parent, we merge the left and the right. Okay, a little thing to notice right here is that whenever we do a merge, it is always that we are merging either the left with the empty and the parent, or we're merging the empty, the parent, and the right. It always goes like this. Okay, so yeah, if we were to take the 10 and merge it, this node will now become a 3 and a 10. The root is still 30. It has this link. The left side is going to be 41, and following by the original subtree. The 2, the 7, and the 14, and the 16 right here. And that's it. The tree is well balanced again. Okay, a very quick sum up for a 2-3 tree. In the searching part, it works just as all other search trees. The root is here. The left side is less than the value of the root. The right side is greater than the value of the root. This is the searching part. And for the insertion part, we see that the tree only grows whenever a node overflows. So only when a node overflows, it performs a split operation, will this make the tree grow taller. And with this trait, we can observe and see that because of this, all the leaves are at the same level. All the leaves are at the same level at all times, because it only grows from the bottom to the top. Unlike in AVL trees, we might have some tree look like this, and here's a dangling node in AVL tree in this case. But in a 2-3 tree, a dangling node is not allowed, because the tree will automatically deal with this with either borrowing from a sibling or getting a node down from parents and merge it. And for the deletion part, we always assume that we're dealing with a leaf. If ever a node that is being deleted is not in a leaf, we move a leaf to that spot, and just like how we do it in a binary search tree. And after we move this thing to the bottom, to the leaf, we now either borrow from sibling or we merge from parent. And notice that whenever we merge, we take a node from the parent, and we are always merging with a valid node with an empty node. Always there's just an empty node, because that's how it works, right? We have an empty node and we merge an empty node with the parent node. Oops. Yeah, and that's basically it. Thank you. Oh yeah, there is a really great fact about learning a 2-3 tree. So every 2-3 tree has a 1-to-1 mapping to a left-leaning red-black tree. So once you've learned how to do a 2-3 tree, doing a red-black tree will become extremely easy. And I'll soon do a video about that. Thank you.